Welcome to the second lecture in mathematical statistics. Since there's now one person who does not understand German but does understand English, I change again back to English and give this lecture in English. Sorry for the slide which I have here because I didn't know it. It's in German, but I will translate it. This is about what did we do the last time. We talked about the principles or what we do in mathematical statistics. What we do is we have observed some value from a distribution and we want to get some information from this about the distribution. There's the classical parametrical statistics where the form of the general distribution is given, and this form depends only on finally many parameters, and then if you want to estimate it, you can just estimate values for these parameters, which makes the estimation problem more simpler, because instead of estimating this huge high-dimensional object of a distribution, you just have to estimate these finally many parameters. But of course it has so there's one big advantage, and if this form is right and you know the form, then this is basically the best thing you can do. But on the other hand, application, you usually don't know the form of the distribution, and if you start with the wrong form of the distribution, then you might end with an estimate which necessarily has a large error. So there's also the non-parametric statistics, and that's what I'm doing in my research, and where I will also make a lot of results in this lecture, where the underlying distribution cannot be described by finitely many parameters. And then we have seen, or I've described, three problems which we deal with in non-parametric statistics. The first is the estimation of distribution, which we start today. The second one is the estimation of density, which we will do after that, before we do the classical parametrical statistics. And then the third one is the estimation of regression function, which we will deal with basically in the next lecture about deep learning. Okay, first part. Questions so far? Then let me start with the... I think I need a little bit more light. And we start with the estimation, chapter 2, estimation of distributions. We have IID random variables x, x1, x2, and so on with values in RD. I denote by nu the distribution of x. That means that mu of x is the probability that u of some, so mu is some function from the Borel, set of Borel measures in Rd to R plus, so that mu of a set B is Px of B is probability that x is in B. So that means mu of B is Px of B, which you all know is the probability that x is in B, or in other words, the probability of the pre-image x with exponent -1 of B. Given our realizations of the random variables x1 to xn, so you have observed value of these independent identical distributed random variables, and the aim is to construct an estimate mu n hat, which depends on this given realization of mu. And this estimate itself is also a function of from BD to R plus. Or more generally, it could be also a function to R, because it might, even if you know that the object to be estimated takes on only positive or non-negative values, it might make sense if you sometimes allow negative values too. So I write it in a more general way. So this one is an estimate of the probability. Could I estimate? No. That was of mu. And clear, for each set, you have that mu n hat of B is an estimate of mu of B. For each set B aus BD, you have that mu n hat of B. And again, it's mu n hat of B and the realization x1 to xn of capital X1 to xn. This one is an estimate of the probability mu of B, and that is equal to Px of B. P of x in B. And the first estimate which I will introduce here, and that's the standard estimate. How do you estimate the probability? Well, if you given realizations of the distribution, or given a sample consisting of IID values of the distribution, or realization of IID values of the distribution, well, you just estimate the probability by the number of points in your sample which are in a set B divided by n. And that's the empirical distribution. And that's the first section which I will introduce here. And we start with the definition. That's definition 2.1. Let x1 to xn be in RD. Then un that's this time a function to R plus. As you will immediately see, mu of B is the arithmetic mean of the indicator function of the set B evaluated at x1 to xn. So it's 1 over n, I equal 1 to n. And for this indicator function, I write capital I, index B. I will explain this notation in a moment. And this you can also, but it's small xi here, sorry. Because we define at the moment the empirical distribution to values small x1 to xn. So that's the same because, okay, I should first explain what this indicator function is, and then give this formula. So just leave a gap here at the moment. This is the so-called empirical distribution of x1 to xn. Empirical distribution. And now I explain my notation, this IB of x. Is either 1 or 0. It's 1 if x is in B and 0 else. And then it's easy to see what you do here. You sum up for each x1, xi, which is in B, you get a 1. For all other one, you get a 0. So this whole sum is just the number of xi indices I from 1 to n where xi is in B. And I write this as this form for indicating that I mean the cardinality of the z, or the number of points in there. Xi in V divided by n. There's no point here, sorry. And it's easy to see that this empirical distribution is indeed a probability measure. It's a distribution, it's a probability measure, because if you look at this function where B maps to indicator function of the set B evaluated at the point xi, that's just the Dirac measure to the point xi. This Dirac measure is a probability measure, and then it's easy to see that if you make an arithmetic mean of a probability measure, you get a probability measure. Do you have a question? You can ask in German or in English, doesn't matter.
No, it's fine.
No question, sorry. Okay. Any other questions? Okay, then let me just write it. It's easy to see that mu is a probability measure. And that's since it's an average of Dirac measures. Or since it's the arithmetic mean. And let me repeat it, I guess you all know it. What does it mean that it's a probability measure? It means we have that the values are always greater or equal 0. The value of the complete set for the sample space RD is 1, and you have the sigma additivity, it has mu n of a union of pairwise numberable union of pairwise disjoint Z is just the sum. That's Bn for all pairwise disjoint. Okay, and then it's also, if your points x1, also easy to see, or obvious, if your points x1 to xn are pairwise disjoint, then mu n of the sets containing only one of the xi is just 1 divided by n. If x1 to xn are pairwise disjoint, xi is 1 over n. So you distribute, when you estimate your distribution, you distribute the mass 1 among the set Rd, and where you put measure 1 over n to each of the observations. Question?
Warum kann unser Schätzer mit Dach negative Werte haben?
Warum kann unser, why is it possible that our estimate can take on negative values? Well, at the moment not. Here, not there. But in a general problem, it might make sense to allow this, because it might be that I get better estimates, or estimates which converts in some situations faster if I allow also negative values. But that's a general question. Does it make sense to estimate a value where you know it can take on only non-negative values by something which can also take on negative values? But it might be that in some situations it's faster. That's easier. Any other questions so far? Okay, and more general, we have this formula here. I don't write it again. Yeah? Mu n of b is this number of indices between 1 and n, where xi is in n divided by n. Now what we are interested in is, can we say something about the quality of the estimate? Can we say something about the properties? And the simplest thing is to consider that just some fixed set B from the Borel sets, and consider mu n of b as an estimate of mu of b, and what happens if n tends to infinity. And then the strong law of large number implies mu n of b converge almost surely to mu of b. And now I want to study how good is this estimate in some theoretical framework. And for this I replace the realizations x1 to xn by the random variables, capital X1 to capital Xn. And then my whole estimate is some random quantity, depending on this random variables, and then I make some. Then I look how does this random variable behave for n tending to infinity. So let mu n be the empirical distribution of x1 to xn. And that's something which we often will do in mathematical statistics, because we want to study some mathematical properties of these things. And then, of course, you cannot say something about all realizations, because there will be some realizations which have which occur only with measure 0, or some small subsets of relation which have measure 0, and it might be that the estimate behave anyhow on these realizations, but instead we consider what happens if we put in the random variables. Can we say something about the random quantity which you get then? So if nu is the empirical distribution of capital X1 to Xn, then the strong law of large number applies for each B aus BD. If I look at nu of B, well, by definition, that's just the arithmetic means of the indicator function of the ZB evaluated at the x1 to xn, capital X1 to xn. And if we look at these indicator functions, well, these are random variables. They are identically distributed, because the x1 to xn have the same distribution. They are independent because the x1 to xn are independent, and consequently also functions applied to the x1 to xn are independent. And they are integrable because they are bounded. So you have independent, identical distributed random variables which are integrable, then you know by the strong law of number that converges to the expectation. Almost surely with probability 1. Since these random variables no, I need the whole sequence. They are IID and integrable, independent, identical, distributed, and integrable. And then you see this indicator function. Well, the expectation of this one, well, that's just, it takes on only two values, 1 and 0. It's just 1 times the probability that it's 1. So that's 1 time probability that x1 is B, and that's mu of B. And that I call formula 2.1. And what I want to do in the sequel, I want to tightening this statement. Tightening of this statement. And one way to do this is to consider the cumulative distribution function of mu n, and that's I first consider the cumulative distribution function of mu, and then we will use the cumulative distribution function of un to estimate the cumulative distribution function of mu. So let capital F be the cumulative distribution function of mu. And I will use the abbreviation CDF of mu for that. That means f is a function of Rd to R plus, or the interval 0, 1, and f of some x is mu of the interval from minus infinity to x. And now I have to explain to you what this interval is in case that the dimension of d is greater than 1. Well, that's just the cross product of the intervals minus infinity to the first component of x with minus infinity to the second interval of x, and so on. So, wherefore if I use x and I write the vectors as x1 to xd, where this 1 to d are the upper indices in brackets, and then minus infinity to x is minus infinity to x1 times minus infinity to xd. And you all know from probability theory that f is important in the sense that f uniquely determines the distribution of x. We know from probability theory u is uniquely determined by f. Which means that the probability measure nu von id nach 2a plus b maps to u of b is uniquely determined by, if you don't just know the values of it from this half of an interval. So by minus infinity to x maps to u of minus infinity of x for x in Rd. And so this is somehow important function related to the distribution, and now we want to estimate it, and the straightforward thing is to estimate it by the empirical, by the cumulative distribution function of this estimate of the distribution. So we can estimate f by the CDF of mu n. And this CDF of mu n has a special name. It's the empirical cumulative distribution function 2x1 to xn. Or did I want to write off or 2? Did I write here? No, off. I want to write off. Okay. Definition 2.2. 2.2. The CDF of mu n and that we will call from now on Fn, capital Fn, from Rd to R. Fn of x, un of minus infinity to x, it's 1 over n, some I equal 1 to n, indicator function to the set minus infinity to x, to xi. This function is called empirical cumulative distribution function of x1 to xn. And the first result, which we will look at in this lecture, is how well is this estimate. You see immediately from 2.1, if you plug in here the interval of minus infinity to x, then this converges to mu of minus infinity to x. So pointwise, which means Fn of x converges to f of x almost surely. So you have a pointwise convergence. And then the first theorem which we consider as the fundamental theorem of mathematical statistics says that you have here even this uniform conversion. So the supremum over all x in Rd of absolute value of the difference of Fn of x minus f of x converges to 0 almost surely. But before I explain this to you, or are there any questions to that point? Question, please.
What is the difference between a distribution function and a cumulative distribution?
Where's the difference between a distribution function and a cumulative distribution function? Well, that's the distribution function. So in German it would be Verteilung.
Yeah.
And the cumulative distribution function in German would be Verteilungsfunktion. Okay? And then I think it's clear. Huh? Oh. Oh, you know the difference between Verteilung and Verteilungsfunktion, huh? The distribution function itself, well, that's a measure on BD. Yeah? And the cumulative distribution function is just, this describes just the values of this measure on some special set, namely the intervals from minus infinity to some point x. All these sets, yeah? And this is easier because the first thing, there you put in sets. And then you have a function where you can put in sets. You cannot make a sketch of it, for instance, or make it draw it, yeah? But the other one, that's a function where you put in a point, and especially if d is equal to 1, you can simply draw it, yeah? You know the cumulative distribution function of the standard normal distribution, yeah? It's a nice function you can, but you cannot draw the normal distribution. You can draw the density, yeah? If a density exists. But this you can even define if there is no density at all. Okay? We didn't focus so much on it on probability theory, but it's and the important thing is we had this theorem in probability theory. I didn't prove it, but it goes back to Maxwell theorem, and I mentioned it. Yeah, there are some theorems about measure which you say, okay, when on which sets are the or which function values already uniquely determine the measure. That's one of these points that it's already uniquely determined on the sets. Any more questions? Okay, then I need a little bit of time to clean the blackboard. Give me 5 minutes. My clock it's now 10:33, so I will go on with the lecture on 10:38. Okay, let me continue with the lecture. So I already told you what we had before. Relation 2.1 implies that this cumulative distribution function, if you consider the cumulative distribution function of capital X1 to Xn, so of the random variables, then it converges pointwise almost surely to the cumulative distribution function of mu. So if Fn is the empirical cumulative distribution function CDF of capital X1 to Xn, then 2.1 implies for all x in Rd Fn of x, and you can also either you conclude it from 2.1 or you make the same proof. It's 1 over n times sum I equal 1 to n indicator function to the z minus infinity x to xi. Now again you have IID random variables which are integrable and the arithmetic mean by the strong law of numbers converges almost surely to the expectation. One of them, and that's the probability. So this indicator function is 1 if capital X1 is less equal than small x. So that's the probability that X1 is equal to small x and that's equal to f of x. And that's relation 2.2. And more generally, we have the following theorem. And let me what is in this part. That's theorem 2.1. And it's the Klivenko-Cantelli theorem, or also called the fundamental theorem of statistics. Let x1, x2, and so on be IID, RD value German variables with cumulative distribution function f. And let Fn be the empirical distribution function to x1 to xn, or of x1 to xn. Cumulative distribution function of x1 to xn. Then the following holds. We consider the supremum over all x in Rd. Fm of x minus f of x, absolute value, and even that converges to 0 almost surely. And I will not prove this directly. It's part of your first practicing course to give a direct proof. It's not difficult to give a direct proof. So, because you have a pointwise conversion here, and then you have this limit function, has some nice properties. It's monotone, it's monotone and bounded, I think, is enough. And the continuity from the right you also need, and then you can show that you even have using this that you have even have uniform conversions. But it's a little bit technical to make it in this way. Instead, we will give the proof in a more general setting in the next section. So I reformulate it in a much more general setting and use the so-called Wapnick-Jovanenki theory to prove it there, and then the proof is more urgent. So proof will be given in the in the next section. In a generalized setting. So sometimes it makes sense to prove something much more general to get an easier proof. Even if this much more general proof is more complicated, but it's sometimes a lot more logical and less technical, or maybe more straightforward. Okay, questions? So far. That's section 2.2, WiSe theory. And WiSe is the operation for two Russian mathematicians, Wapnick and Jovanenki. And the first observation is that I can reformulate theorem 2.1, and I'll reformulate it as follows. We can S, and I just replace the empirical distribution function and the empirical cumulative distribution function and the cumulative distribution function by the empirical distribution function and the distribution function of some proper set, and the proper set is this interval, which used in definitions. So basically, this is the supremum over sets A, where I have to tell you what A is, comes in a moment, of mu n of A minus mu of A. Let's converge to 0 almost surely. 3. And then I just choose for the sets A, I choose a proper subset of the set of all subsets of RD, so the power set of RD. And that's I write with calligraphic A. And then in our case, if you want to get the theorem 2.1, just A has to be the set of all sets minus infinity, interval minus x, x is an RD. And what we do in this section is, instead of proving 2.3 for this special set of subsets of RD, we prove it in a more general ways. So in the sequel, derivation of sufficient condition for 2.3 in case of general A. In case of general subset A is a subset of the power Z. RD. So we consider the question, can we say for which subsets calligraphic A of the power Z of RD does 2.3 holds? Can you give me any example, such as this holds, where you can prove it? Do you know any subset of the power set of RD, such as 2.3 volts? The empty set and the full set. So the empty set, it depends on how we define the supremum over the empty set. I'm not sure. But might be the supremum might be plus infinity, but I'm not sure how to define it. Maybe we ignore this. And the full set, you mean the complete power set from RD?
No, I meant the set of where the empty set and RD are part of the pure sigma algebra.
Where the empty set and RD are part of the. So you consider A just to be two sets, the empty set and the. Okay, I know what you. Okay, I understand what you mean. The first thing is you propose I choose for calligraphic A just the subset which contains only the empty set, yeah? And then it's clear mu(n) of empty set is 0 and mu(n) of A is 0, yeah? That's right. And the second set is you consider the complete RD, yeah? And then you have mu(n) from RD is 1 and mu of RD is 1 and the difference is also 0, yeah? That's complete. And then you also can put them both in there, yeah? Okay, anything else? That's right. But more generally, well, do you know any sets besides the empty set and the set RD where mu(n) of the set converges to mu of the set?
x1 to xn.
x1 to xn. You think that at x1 to xn depends on, do you mean the fixed x1 to xn, so or do you mean the random variables?
I think I mean the fixed point.
The fixed, so I mean fixed point, x1 to xn. Well, for fixed points, it's true. Why it's true?
The points we constructed them.
Well, if you put in the points which we constructed in there, at the moment, yeah, we put in the random variables, yeah, x1 to xn, yeah. If you put them in there, then you have here mu(n) also always 1, yeah? And if mu is a measure which has a density, then all finite sets have measure 0. So actually, you prove the counterexample. You make a nice counterexample that if I plug in here the power set of RD, it will not work. That's also interesting, but I was asking for a much simpler thing. If you think what we have talked about in the previous 70 minutes, what did you know about the empirical distribution? What did you learn about the empirical distribution until that point?
If you have more sigma measurable sets, it converges to the distribution function.
If you plug in any Borel set, then this difference converges to 0. Yeah? So immediately you see, if you use capital A to be any to contain just one set, and doesn't matter what the set is, yeah, then this will hold, yeah. And then you also see, of course, if it works for one set, it works also for finitely many, yeah. Because the supremum over finitely many is less than the sum of the distance, yeah, and each interval distance converges to 0. So for any finite subsets of the power set, it converges, yeah. That's the first thing which I would like to make a point on. But now we want to generalize it to much infinite sets here. And what Czerwonenkis did, they proposed to consider some geometric property of this set calligraphic A. And that's what I will define next. It's the so-called shadow coefficient. And that gives definition 2.3. You let A be a subset of the power set of RD, and A should not be the empty set. So at least one set should be in there. And consider n and n. N is a natural number. And then I define some property of the subsets of RD, of calligraphic A, which has nothing to do with the distribution. So nothing to do with randomness. And that's then SAN. It's the nth shadow coefficient of A. And this nth shadow coefficient of A described, given any points x1 to xn in RD, how many points can I pick out by sets of A? And picking out means that I can get the subsets of this, not how many points, how many subsets of these points can I pick out of x1 to xn. So I give you x1 to xn, and I want to know, okay, there are at most 2 to the power n subsets of this set, yeah? And how many of them can I write in the form, this whole set, x1 to xn, intersected with some set A of capital A. And the maximal positive number, that's the n shadow coefficient. So I make a maximum over all x1 to xn in RD. And I look at the number of sets which are in the following set. And this following set I construct by intersecting subsets of calligraphic R with my x1 to xn. So that's the quantity which we look at. And this is a ugly quantity somehow, so it's difficult to understand what it's doing. But the nice thing is it has nothing to do with the distribution here. But somehow it describes the complexity of the set calligraphic A. Because if you give finitely many sets, then if you look just at this x1 to xn as a subset of A, yeah, and intersect it, then this decides how many of them are there, yeah. So how complex is if you reduce this capital A to x1 to xn, how complex is it there? Okay, and that's called, this one is called nth shadow coefficient of A. And what we'll show in the sequel is if this n shadow coefficient grows, so all of the logarithms of this n shadow coefficient divided by n converges to 0 for n tending to infinity, then 2.3 holds. That will be the surprising fact. And then we will show we will analyze how big is the n shadow coefficient for our special set, which we consider for the Klimenko-Cantelli theory. So in other words, I've said it already, but maybe write it down because it's not easy to understand what we are doing here. How many subsets of a set of n points can be picked out by sets of A. And picked out means by intersecting the sets with the endpoints. And let me make a few remarks concerning this definition. And the first remark is if you consider fixed x1 to xn in Rd, then it holds. And if you consider for this fixed x1 to xe the number of points or the number of sets in the set A intersected to x1 to xn, A capital A. What are possibility values for this number? Any suggestions? Can you say anything about this number? In which, or about the range of this number? What are possible values?
0 up to 2 to the n.
0 up to 2 to the n. Can it be 0?
If it's you don't set any restrictions on A, it could be a set that is distinct from any of the axes, and so it's the empty set, the intersection.
Yeah, if you allow that it's the empty set, but if I make the restriction that it's not the empty set, maybe make this way. What would you say then?
I mean, can A, small, like normal A, be the empty set?
Normal A can be the empty set, yes.
But
Then this whole thing will be the empty set. But this is a set of sets. And I want to know how many sets are there, and you have at least one, yeah? Okay. So, but what I don't want to have is that this capital A is the this calligraphic A is the empty set. But that was something which I somehow implicitly wrote already, yeah?
Oh, you wrote explicitly on the left.
On the left, yeah. Here it was explicitly written, because otherwise it's not clear what the whole thing is, yeah? But make it this again, and then you see, well, it will be, this is a, well, these are all, what is in there are subsets of x1 to xn, yeah? And at least one subset is in, yeah? Because there's at least one set in here, so at least one subset is in, and then you can consider the possible number of subsets of x1 to xn, or how many subsets can you choose here? Well, and the maximum number is 2 over 2 with power n, but on the other hand, it must be a natural number. So it will be something in 1 to 2 to the power n. That's the first observation we have. And if you have this one, then you see what I compute the maximum over here is some discrete values, and then the maximum always exists. So this is the number of subsets of a set with n elements. And consequently, the function where x1 to xn maps to this number A intersected with x1 to xn, and A in calligraphic A, this function attains its maximum. First observation. And second observation, what we get from this is A implies immediately that this Schroeder coefficient is a value between 1 and 2 to the power n. A implies one is less equal than SAN less equal to the power n for all A. Second point. Third point, what is the relation between, if you keep the set of subsets of RD fixed, so calligraphic R is fixed, but you change n, what happens then? Let's see. And the point is directly from the definition. It follows. Is A and 1, and you consider as A and 2, and I want to give you some relation. 4 and 1 is less equal than 2. So if you give n1 points and look how many subsets of these n points in the best case you can pick out by sets of capital A. And now it's one number of points and 1, and second I give you a bigger number and 2. What happens? Well, the number of subsets is increasing or non-decreasing. And how do you see this? Well, you just can consider if you have A intersects with x1 to xn1, that's not the same as some set B intersected to xn, x1, xn1, then this also implies if you make this set of points larger, so instead of x1 to xn1, I go from I take the same points x1 to xn1, but then I take additional points xn1 plus 1 and so on up to x1 to xn1, xn1 plus 1 until xn2, and this will also not be equal to n1 now you can think about why does this imply my assertion from above. Well, look at S and A and 1. Then you find some points x1 to xn1 where the number of sets intersected with x1 to xn1 and or the number of sets which you get by intersecting sets of calligraphic A with xn1 to x1 to xn1 is just equal the n1's shadow coefficient. Then you find let capital N be the n1's shadow coefficient. Then you find capital N and Z's, so that for these capital N Z's, all, if you plug in 2 of these capital N Z's, all of these sets are not equal. But then below these sets are also not equal, and you see, okay, doesn't matter what I choose for xn1 plus 1 up to xn2, I will get at least capital N, this was the n1's shadow coefficient, many different sets when I compute n2's shadow coefficients. And that's the proof. Okay? So if you want to prove this, you assume that this holds, yeah? Or you assume as you have n1 is less equal to n2, yeah? You consider this quantity, you choose so many sets, such the intersections of 2 difference of these sets always satisfies this relation, then the intersection of 2 difference of the sets always satisfies this relation, and then you know this is the maximum of the sets you get if you choose these points properly, and then this number must be at least as large as this number here. Okay, questions?
Yes,
Yeah, sure.
like for the proof, I want to ask, like, is it not sufficient to say that if the number, like n1 is or the cardinality of the set is still smaller and the intersection, like the number of sets that you can build from the intersection of both sets is then also reduced.
I see. You just make the proof easier, and there's a point here. You can make the proof easier because if this number n2 is larger, yeah, then of course you can basically choose only n1 different points here, yeah. So you choose the first n1 different points, and then all other points which is equal to the last point, yeah. And then you compute this maximum for n2 over a larger set, yeah. You are perfectly right, yeah. Easier proof than, but I try to explain.
It's also key.
It's okay, it's even better. Okay, thank you. So this was a little bit too complicated, yeah? But it's always right, yeah? Also right, yeah? Sometimes you can also give a more complicated proof, but it makes no real sense to give a more complicated proof. Okay, I still have a few minutes left. Then next is a remark about the central theorem of the WiSe theory. And the central theorem of the WiSe theorem, which we will not prove in this lecture, states that either this, so if you fixed the set calculus A, either you have SAN is equal to 2 to the power n for all n, or SAN grows only polynomial in n. So a central theorem, that's our surprise. WiSe theory states for any A, one of the following two statements holds. The first statement is SIN is 2 to the power n for all n in n. And the second statement is SIN grows in n at most polynomially. There exists nothing in between. So you cannot construct a subset of the power set of RD such, for instance, SIN grows asymptotically like square root of 2 to the power n. That's not possible. And I mention here without proof, so I don't give a proof. just want to share it as information. And what they basically introduced, Wapping-Cherwin, is they introduced some even more cryptical quantity than what we did with the Cheddar coefficients. The Cheddar coefficients is more or less clear, but the other thing is the Wapping-Cherwin is the dimension of a subset that's much more complicated or much more difficult to understand what it really means. But it's a combinatoric quantity again, and this is the combinatoric quantity which helps you then to decide about which of these two cases holds and bound these shuffle coefficients more efficiently. Okay, any questions up to this point? Okay, then may I ask again. So, how many people do not speak English, do not speak German at the moment? It's you? Someone else? Maybe we can quickly talk about the premises of this lectures here, that I can explain about probability theory. That's all. But it's clear I will give this lecture in English. Don't worry about it. Okay. So, thank you very much. That's it, and see you again on Friday.